Faraday's law. So we can see as the introduction that the purpose was to explore the results of the application of Faraday's law to a flowing magnet through a foil tube. We do this experimentally, and then we also computationally model it in GlowScript and compare the two. The experimental time, as you can see here, is 1.25, and the computational time is 1.118. So those are both very similar. So the principles and equations that we use is Biot-Savart law, Faraday's law, and Ohm's law. So those are the three main equations. You can see them shown here below. And those are the three equations that we have to use. The magnet was used to model a magnetic dipole. That's one of the principles. And the other principle that we used is assuming that air resistance is negligible in the computational model, and we assume that gravity and magnetic forces are the only forces acting on the magnet. So the system is the tube and the magnet. The surroundings is pretty much everything else, including the Earth. The initial conditions is marking north on a magnetometer and then performing the performing the experiment by dropping the magnet through the tube 5 separate times, recording and then calculating how long it took the magnet to fall and finding the average. So this is the data that we calculated here. Trial 1 was 1.23 seconds. Trial 2, 1.25, 1.31, 1.27, 1.23 for trials 3, 4, and 5 respectively, and the average is 1.26 seconds, as you can see here. So the length of the magnet was 0.30 of the tube. The width was 0.006. The inner radius was 0.03. Mu was 2.21, and the magnet mass was 0.025. So this is the beginning of the code that I used. As you can see here, some of the constants are listed above in the initial lines. Then we begin doing step 1, which is the first part, where we enter the geometry of the tube, and then use some of the numerical parameters that are already given to us. And from there, we create the tube of aluminum foil as a series of rings. Then past that, we do step 2 with inputting some more initial conditions, visualizing the bar magnet just so we can visually see it. And we calculate the magnetic forces from the tube on the magnet, and then having done that, we then calculate the magnetic force on the magnet, and then finally are able to find F net overall, considering F gravity and F magnetic. So this is the plot that we get. The time in the tube calculated was 1.18 seconds, which is very similar. Mu was 4.5. So it was very similar to the experimental model. So the intensity of the coloring is shown with the current. Red is the counter, blue is clockwise, and we can tell that based off of this combination slowing the magnet down. The system, nothing really changes when we flip the magnet around. The currents flow differently, but F magnetic still opposes F gravity, so we would be slowing down as compared to if you just dropped a magnet not inside of a foil tube. So both the model and the real-world version were very similar to each other, so the model was accurate. If we wanted to make it even more accurate, we could account for air resistance, because that is an actual force you have to consider a little bit of. We could also consider more rings in the model. So the forces acting on the bar magnet, at the beginning the forces are unbalanced and then balanced in the flat section, and then the velocity increases where gravitational forces are greater, so they're unbalanced. The experimental and computational model are very similar. Some error however, that we could consider is the fact that we didn't ignore air resistance, as I mentioned earlier. There is some human error just in terms of when you time things, it's not going to be completely perfect. And then also the mu values were a little bit off when you compare the experimental versus the computational model, so that could be part of it. If we reduce the resistivity of the conductor to as close to 0, the induced current would be greater, and there'd be a greater magnetic force. If holes were cut into the tube, the induced current would decrease because those holes disrupt the normal flow, and the force would not be as strong, so it would fall faster. And that is all. Thank you for watching.